In this session, we are going to talk about the third passive element that we can use for designing the passive transducers, that is the inductor or the inductive element. Okay, so induction is the third phenomena which we can use for designing the passive transducers. We have already seen how to use resistance, we have seen how to use the capacitance. Now we are going to see that how we can use inductance to design a passive transducer. Okay, so the most popular transducer that is used using an inductive element is the Lvdt. With the help of an Lvdt, we will understand how we can use the inductive element as a transducer. So LVDT actually stands for linear variable differential transformer. On your screen, you can see a diagram which actually represents the electrical connections of an LVDT, right? This is actually based on the principle of transformer, right? So just like in transformer, we have a primary winding which is connected to the source voltage. Then we have two secondary windings, and in between we have a core. Okay, this is a magnetic core. So if you see this assembly, when you supply a source to the primary winding, there is some current flowing into it. Now in the closed vicinity, when there is a magnetic core placed over here, that core gets, magnetized, it becomes an electromagnet, and further it transfers that induction effect to the secondary coils also, and as a result there is a current developed in the secondary coil as well, right? This phenomena is called mutual induction. You must have studied this in your preliminary classes, that what mutual induction effect is. That is, there is current flowing in one coil and you bring the another coil in close vicinity. So due to induction, there is current flowing in the secondary coil as well, without connecting any power source to the secondary coil. So that particular concept we are using over here, that we have a primary coil connected to the source, okay, and we have two secondary coils, and in between there is a magnetic core. So when we supply current to the primary coil, due to mutual induction, there is a current developed in the secondary coils as well. Now, in the nominal state, the connection is made in such a way that the polarity of the potentials that is developed in secondary 1 and secondary 2, they are connected in opposite to each other. That means if there is equal voltage developed in S1 and S2, the output that your voltmeter will measure will be 0. Okay, that is how this is the basic connection of the Lvdt is made, right? Why we are doing this, we'll just come to that also. There's a reason why we are connecting it like that. So, this we have to keep in mind, that the two secondary coils, they are connected in such a way that the net output that you are getting, that is the output voltage, is actually voltage V1 minus voltage V2, where V1 is the voltage developed in secondary 1 and V2 is the voltage that is developed in secondary 2, right? Now let us see how this works. In the first case, now this coil that you see in between, the core, this core is actually connected to the displacing element of the field, right? So when I connect this core to the displacing element, when the displacement takes place, the possibility is, in this you can see that either the core remains or in its place, or the core may move left or it may move right. That depends upon the displacement, right? So initially the core is placed right in the center. So when it is in the center, the voltages that are produced in S1 and S2, it is equal, and so the net voltage that you get is 0. Okay, over here on the figure that you can see, red color is showing you the excitation that is there in the primary coil. Blue is secondary 1, green is secondary 2, and at the bottom the cyan colored line that you can see is actually the net output. So when the core is exactly in the center, okay, due to the mutual induction, the voltages that are developed in secondary 1 and secondary 2, they are equal in magnitude. But because the connection is made in such a way that the output actually is, S1 minus S2. So when you actually add up the two, you can see that the net result will be 0. Okay, because the polarity of the two is actually opposite to each other. Agar secondary 1 is giving you a voltage of positive magnitude, then secondary 2 will actually give you the voltage of negative magnitude. And when you add these two up, the ultimately at the end, if the magnitude is same, the output will be 0. So you can see that the cyan colored line is actually showing you 0 magnitude. This is the first case if when there was some displacement did not take place. If there was some external force but the displacement did not take place, the core did not move, the core is exactly in the center, so the voltages that have been induced in secondary winding 1 and secondary winding 2, they are equal to each other in magnitude but opposite in polarity. So the net output that we are measuring becomes 0. Okay, now in case 2, what happens is, if you see in this figure, slightly the core has moved towards the left. That means it has moved towards secondary 1. So in magnitude, the blue colored wave, if you see, the blue colored output is now slightly higher in magnitude as compared to the green colored magnitude. That means the voltage developed in secondary 1 is high in magnitude as compared to the voltage that we are getting in secondary 2. And since they are opposite in polarity, the output that we are going to get is V1 minus V2. Now this is not 0. You are getting some value. If you see the cyan colored line, some slight curves you can see. That means there is some voltage coming at the output now. So when the core has moved towards one side, the balance has got disrupted. Secondary 1 now has a higher voltage magnitude as compared to secondary 2, and because of that the resultant that we are getting is V1 minus V2. That means we get some positive value. Okay, some output we are getting. Now the third case could be that your coil is now moving towards the secondary 2. That means towards the right hand side. So if the displacement is actually resulting your coil to move towards the secondary 2, the magnitude of voltage in secondary 2 now becomes larger than secondary 1. Okay, so the net output voltage, now if you see in the cyan color, you can see some voltage coming in. This output is actually V2 minus V1 because the voltage in secondary is larger as compared to the voltage in secondary 1. Okay, so the output that you will get will be V2 minus V1. Okay, so basically what we are doing is, this core is movable. The core is connected to the displacing element. Okay, whatsoever the displacing element might be. So that displacing element, when it, some displacement takes place, it moves the core either on the right side or on the left side, or it may stay in the center. Okay, and corresponding to that, the voltages that are developed in secondary 1 and secondary 2 are varied in terms of magnitude, and the output that you are getting, that is the difference of the two voltages, will be dependent upon whether V2 is greater or V1 is greater. Okay, you can see all the stages together. Like in stage 1, we had the core exactly in the center. Two equal voltages of opposite polarity were being generated in secondary 1 and secondary 2. So the net output was 0. In stage 2, the core, it moved towards the left hand side. So there was, a higher voltage magnitude in secondary 1. So when you subtract the two, you get some slight voltage at the output, because the magnitude of secondary 1 voltage is higher than the voltage at secondary 2. And in stage 3, when your core, it moves towards the right hand side, that is secondary 2. So what happens is that the magnitude of secondary 2 is now higher than secondary 1, and so the output that you will obtain will be V2 minus V1. Now, when you design an instrument, if you want to keep the output formula fixed, suppose we have fixed V1 minus V2. So what will happen in stage 2, when actually V1 was higher than V2, you will get a positive output, right? But in stage 3, when V2 is higher than V1, so what will happen is the output that you will get will be of reverse polarity, because now V2 is higher. So V1 minus V2 when you do, so you will get some result in minus polarity. So that when you will represent in terms of waveform, the voltage waveform will be of opposite polarity, right? So like this, the output voltage, we can measure the displacement in terms of voltage with the help of mutual induction. Okay, now in this figure you can see the figure on the right hand side is actually showing you that as the core is moving from center towards left, now see it is moving towards the right hand side. So when it is moving towards right hand side, the blue becomes larger in magnitude and green becomes small. Now it's moving towards left, so green becomes large, and so correspondingly your output is changing. As there is movement taking place, correspondingly you are getting a corresponding output voltage, right? On the left hand side, this is what actually the manufactured, when you manufacture it in terms of a sensor or a transducer, this is what it looks like. There's a core in between which is attached to the moving element. When it moves, so you can actually measure the voltage deflections. So this is how you can use the concept of mutual induction to measure the displacement. Okay, now this displacement can actually again be further connected to maybe pressure, maybe strain, maybe force. If there is some force being applied, force is resulting into displacement, displacement is resulting into electrical voltage due to mutual induction. Likewise, you can use this concept for designing the passive transducers in a variety of applications where we can connect the physical parameter to the mutual induction concept, and the output will be reflected in terms of change in voltage. So we can see that we have a lot of advantages of using an LVDT. It has a infinite resolution. Okay, it has very high input. LVDT has a very high sensitivity, because even a slight movement can actually introduce a large change in the mutual induction. It has very good linearity. That means there's a linear relationship between input and output. It's very rugged. That means it's quite robust to use. It provides less friction, almost zero friction. It has only there is slight air friction when the core is moving. It doesn't have any hysteresis, and it gives very low power consumption. So we can see that LVDT is actually a very useful passive transducer, which can be used in a variety of applications where we can connect the physical quantity to displacement, and then displacement can be converted into a corresponding voltage.